Last time we talked about Riemann sums. Our mindset is we're after area. And so hopefully, fingers crossed, by the end of today, we'll have a way to find area. Even if it's not a great way, we'll have a way. If not, we'll be there early on Monday. So let's start with our review problem, which says approximate the area under the curve f of x equals 5x squared over x squared plus 4 for the interval from 1 to 7 using a Riemann sum with 3 equal-sized subintervals by using the midpoint of each subinterval. So remember, the idea of Riemann sum is we're breaking up our intervals into equally sized pieces, and then we have to decide a point for each subinterval. Okay, so the potential answers, 10, 13, 16, 19, or 22. What's the answer? E is the answer. Okay, so how do you do this? So what you do is we have 3 subintervals. What it really says is we're going to make 3 rectangles. Now, why rectangles? Because we know how to compute area. We have a high degree of confidence the area of rectangles. So we need to know their widths. So they all have widths too, because we take 1 to 7 and split up into 3 equal parts. That gives us widths of 2. So that's where these 2's are from. Those are our widths. For the heights, we use the value of the function. And that's where they told us to use the midpoint. So the midpoint between 1 and 3 is 2. Between 3 and 5 is 4. Between 5 and 7 is 6. So we're plugging in height at the function at 2, height the function at 4, height the function at 6. And so we evaluate, simplify, combine everything, and we get 22. What's the actual area? We'll get to that. Before the semester is done, this is one that we can solve. All right. So, thought for today. The essence of mathematics is not to make simple things complicated, but to make complicated things simple. And you're probably thinking like, that doesn't sound like my math class. Because math often feels complicated. And the challenge, of course, is that we're trying to answer complicated questions. But how do we answer them? Well, we start by saying, if you have a big problem that's complicated, make it simpler. You don't always have to solve every problem in one step. Most problems can't be. The way you make progress is to say, how can I make this problem a little bit easier? Then repeat, and repeat, and repeat. I oftentimes think of algebra as saying, look, what's the goal in algebra? The goal in algebra is to make things simpler. And if you keep making things simple enough, you get your answer. So when in doubt, keep things simple and try to make things simpler. Okay. Now, we could continue with Riemann sums, or we could do a practice problem finding antiderivatives, in case we wanted to brush up on that. Which one do you prefer? Antiderivatives? All right. You brought this on yourself. No. This is actually useful. So find the integral of 2x cubed minus x squared plus 2x minus 3 divided by x squared plus 1. Okay. Now, first impressions. What are you thinking? Being very zen. You're just being in the moment. Normally, when we see lots of addition and subtraction upstairs, we're like, hey, no worries. I see addition and subtraction upstairs. I'm okay with that. That's cool. Those are the good kinds of addition and subtractions. But what else is there? There's something downstairs. That is the bad kind of addition or subtraction. because you cannot break up addition or subtraction in your denominator. There's no easy way to do it. Can't do it. Would not be prudent. So what can we do? Do we have an avenue, a way to attack this problem?
Make it calculus friendly. Make it calculus friendly by putting a common stuff on the top.
Well, it's not quite calculus friendly that way. Of course, if you hang around me long enough, you might say, I see an x squared plus 1 downstairs. I'm suspicious. Especially if Steve's involved. Steve has an unhealthy fascination with a particular function. All right. So, any suggestions on how we can start this problem?
For some reason, I think I want to factor out the negative from the top.
You can do that. How does that help us?
I don't know, I just let's use division.
Ooh. Division. Ah. Division. We could do division. It might take us a long time, but we can do it. All right, so let's do some division. Long division. Do you remember how to divide one polynomial into another polynomial? Good. So it's time for us to remind ourselves. Now you might say, this seems cruel, Steve. It's on the quiz next week. So if you look on the quiz, the last problem, you have to do long division. So better we learn it now than in real time when you're taking the quiz. Okay, so how does it work? You say, well, I'm dividing by x squared plus 1. So take x squared plus 1. Divide into 2x cubed minus x squared plus 2x minus 3. Now the good news is this should not take too long. The bad news is we still have to do it. All right. Now, how do you handle this? The thing is, you don't have to worry about most of the terms. You only focus on the leading terms. So look at the leading terms. Currently x squared and 2x cubed. Ask yourself the question, what do I have to multiply x squared by to get 2x cubed? 2x. That wasn't a hard question. So, okay, we write 2x. Now, at this stage, take your 2x and multiply by what you divide by. 2x cubed plus 2x. And you might say, that's suspiciously close to what I have. You know, the 2x cubed looks a lot like the 2x cubed. Exactly. You now subtract. Okay, so what happens? 2x cubed minus 2x cubed? Oh, whoops. I should put the 2x underneath the 2x. 2x cubed minus 2x cubed? Gone. Minus x squared comes down. The 2x minus 2x? Gone. The minus 3 comes down. So this is what happens after one step. So we looked at our leading term. We said, we need a 2x. And then we said, what's left? Okay, now the next step is to say, look, just focus on the leading terms of what's left. I have x squared. I have minus x squared. What do you multiply x squared by to get minus x squared? Negative 1. So now I'm going to multiply x squared plus 1 by negative 1. Minus x squared minus 1, and then subtract. The minus x squared subtract minus x squared cancels, gone. Minus 3 subtract minus 1 gives us negative 2. Now at this point, we stop. We stop once the power of what's left is below the power of what we're dividing by. So we have 3 pieces. This is what we got from dividing. This is our remainder, what we couldn't account for, and of course what we divided by. So all this is to say, this is equal to what we got here, 2x minus 1, plus the remainder, which we couldn't get, divided by x squared plus 1. We haven't done any calculus. We've all done algebra. This is all algebra. Now, is this something we can integrate? We don't even have to try too hard, right? Because we have 3 pieces. The integral of 2x, do we know that one? X squared. Minus, what's the integral of 1? X. The minus 2 comes out. Constants just float in front. What's the integral of 1 over x squared plus 1? Arctangent of x. Anything else? Plus c. And we're done. Now, if you enjoyed this problem, I've got wonderful news for you. Next semester, you'll have a whole day, a whole lecture where it's just this, all this, and more. It's everybody's favorite topic. It's called partial fractions. So something to look forward to next semester. All right. Any questions? Okay. So let's do another Riemann sum type problem. We'll do this one. All right. For the function f of x given below, so here's f of x, use a Riemann sum to approximate the area under the curve y equals f of x for the interval from -1 to 1 with 4 equally spaced intervals and using the right endpoints of each interval. Okay, so even though we have the function, let's not stress about it quite yet. First off, let's sketch our interval. We're going from -1 to 1. How many pieces do I want to cut this into? 4. Because they tell us 4. And it's going to be equally spaced. So in other words, we're not going to do like cut, 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 boom. So we cut this in half and then in half again. Well, let's figure out what's halfway between -1 and 1. 0. Okay, how about this point? Where is that? -1/2. And here? +1/2. Okay, so we've cut or split the interval from -1 to 1 into 4 equal slots, 4 equal sub-intervals. Now, we carefully look and say, which point do we use for the intervals? What do we do here in this case? We should choose the right. So, when I'm in the interval from -1 to -1/2, which point am I going to be using? I'm going to be using the one on the right, -1/2. From -1/2 to 0, which one do I use? The right, which is 0. 0 to 1/2, use 1/2. 1/2 to 1, use 1. So our 4 rectangles, and the Riemann sum is all about adding up rectangles. The area, well, it's width times height. What's our width? 1/2. So width is 1/2, height, f of -1/2. Plus width of 1/2, f of 0. Plus width of 1/2, f of 1/2, plus 1/2, that's our width, height f of 1. So if you have 4 equally spaced intervals, you should have 4 terms. Each term corresponds to one rectangle. Now we need the function. So at this point we look at the function. Okay, so what happens when we plug in negative a half? What do we get? We get 2. Negative a half squared is the same as a quarter minus a half. We'll simplify that in a second. What do we get when we plug in 0? Do you see that? Can anybody see what the value is? 0, right? Because it's 0 minus 0. No, x is less than or equal to 0, and 0 is less than or equal to 0. Now for a half, we have to switch gears. When we plug a half in, we have to use our other definition. So it's 12 minus 12 times a half squared, which is a quarter, plus a half. When we plug in 1, what do we get?
0.
0. Because it'll be 12 minus 12. Okay. 2 times a quarter, also known as a half, plus a half, tells us that this first value is 1. So we have 1/2 times 1, which is a half times 0, which is 0. 12 times a quarter, 3. 12 minus 3, 9. So plus 9 halves plus 0. A half plus 0 plus 9 halves plus 0, also known as 10 halves or 5. On a side note, this is an exam problem. You're like, I could do this exam problem. Cool. We want you to be able to do all the exam problems. All right. Any questions? Okay. In that case, here's another problem. Let f of x be a continuous function satisfying, we have some x values, 1, 2, 3, 4, 5, 6, 7, 8, and we have some corresponding f of x values. Now, the only reason they mention it's a continuous function is so that it makes sense to say that there's an area. We really don't care that much about it being continuous. We just need to know what's the value of the function. So the problem, use a Riemann sum with 3 equal intervals to approximate the area under the curve for the function g of x, which is x times f of x over 2, where x goes between 2 and 8. And now I see I left a part out. Which part did I leave out? Yes, I left out, should you use the left, the right, the middle? Well, let's go with the left. Use left endpoints. All right, so 40. Okay, so split 2 to 8 up into 3 equal parts, so you have widths of length 2. So all your rectangles have width 2. You're using your left endpoint, so that's 2, 4, 6. So our area is width times height, 2 times g of 2. That's g of 2 is the height. 2 times g of 4, that's the height. 2 times g of 6. How do you get your g's? You plug it in. So recall, you can't see it because it's hidden right now, but g of x is equal to x f x over 2. So you get 2f of 1, 4f of 2, 6f of 3. How do we get f of 1, f of 2, f of 3? We've got a table. So we put those values in, and we get 40. All right. Good times. Okay, so I'm optimistic that you're going to do great on the Riemann sum problem, because there's going to be one on the exam. You just know it. All right, so now we're running into an obstacle if we're going to really go for it, right? Because the problem is, in order to get good approximations, we can't just use 3 rectangles or 4 rectangles. We've got to use many rectangles. Lots and lots and lots of rectangles, like a ridiculous number of rectangles. And so we want to find a way to write them down, because we don't want to fill up pages and pages of each individual rectangle. So we want to have a nice notation to help us compress the expression. So there's a lot of places in math, you've probably seen this before, where you'll see what's called the dot, dot, dot. Now, dot, dot, dot is shorthand in mathematics to say the pattern continues. But we'd like to not even have that. So we're going to say, okay, so if I have a sum of a bunch of things, I'm going to write it with the following notation. So we're going to use sigma. This is the Greek letter sigma. It's a capital sigma. Why sigma? Well, because sigma starts with S. S for sum. We're adding stuff up. So the theme of this portion of the class, and it's going to continue for the next few weeks, and it's going to spill over into Calculus 2, is we are adding stuff up. So S for adding, S for summing. Now we say, okay, we're adding up a bunch of terms. We have an index, which is going to vary. So this K is going to range over some values. We start at P, so P is where we start our sum. Q is where we end our sum. I sometimes call it a dummy variable. It's just for bookkeeping. And so we can change it. One of the great tools is saying, oh, I can change K if I need to. I just have to update my expressions accordingly. Finally, we know where we start, we know where we stop, and then we say, what are we adding? So that's the A sub K. So A sub K is what a typical term looks like. And in particular says, you give me a value for K, I give you a corresponding number. So it's expressed using K in some way, shape, or form. So we have a bunch of sums we'll go through and practice here. But essentially, when you see this notation, you'll say, the sum from K equals P to Q of the expression, in this case, A sub K. So here, this says sum K equals 2 to 6 of K minus 4. So what's the first term? We start at 2. The first term in this sum, plug 2 in. 2 minus 4, also known as negative 2. 2 minus 4. Okay, what's the next term going to be? Yeah, now you go up to 3. 3 minus 4? Negative 1. What's the next term? K equals 4, which is 0. The next term? K equals 5, which is 1. The next term? K equals 6, which is 2. And then stop. So we started at K equals 2, went to K equals 6, and for each value for K, we got a number. Now notice there's no K's here. K's vanished. K is just a convenient way for us to keep track of things. It helps us compress our notation, but it won't show up in the actual sum once we've worked it out. Okay, how about this next sum? We're starting at 3 and going to 7, and it says whatever thing you're adding, square it, your index squared. So what's the first term? Well, the first term would correspond to when K equals 3, and at K equals 3 we get 9. What's the next term going to be? Would be 16. That corresponds to K equals 4. And then? 25. That's the K equals 5. And then? 36. 6 squared. K equals 6. And then? 49. And then? stop, right? The sum stops. Now, if you're like, oh, I don't want my sum to stop. I want it to keep going. Have I got good news for you? Calc 2 is going to be a blast. All these things to look forward to. You're like, man, I can't wait for next semester. And you don't have to wait very long. 2 months, it'll be here. Okay. Any questions? Looking good? All right. The next sum. We're starting using I. Are we allowed to change the symbol? Yes. Just like we can integrate with respect to x, we can integrate with respect to theta, we can integrate with respect to t. We can use any symbol in our sum. So that's okay. So what's the first term going to look like? Be 9. When you plug in 1 plus 2 squared is 9. What's the next term going to be? 16. When you plug in 2 plus 2 is 4. 4 squared is 16. What's the next sum? Oh, sorry, next term. 25. What's the next term? 36. What's the next term? So 5 plus 2 is 7. 7 squared, 49. And then? That's it. Now, do you notice anything about what we just wrote down? Are you experiencing a sense of deja vu? Have we seen this before? Maybe just above it. These are equal. Is it possible for two sums to be equal? Sure. You might say, but they don't look alike, right? Well, because we've changed. Essentially, this is a shift of an index, is what's happened here. And if you like shifting indices, wait until differential equations. Oh, it's a good class. Good class. All right, let's power through and do these last two. So do you get the feel of what's happening here? Just start at the beginning. It's a very good place to start. And just work it through. So, I wrote down J. I should have written down K. I apologize about that. There we go. So, for K equals 0 to 5, 2 to the K over K plus 5. So at K equals 0, 2 to the 0 is 1. 0 plus 5 is 5. For K equals 1, 2 to the 1 is 1. And 1 plus 5 is 6. 2 squared is 4. 2 plus 5 is 7. 2 cubed is 8. Then we are at 0, 1, 2, 3. 3 plus 5 is 8. 2 to the 4th is 16. 4 plus 5 is 9. 2 to the 5th is 32. And 5 plus 5 is 10. So you can get complicated expressions. They can be extremely complicated expressions, but even just mildly. Okay, our last one here. M goes from negative 2 to positive 3. 1 6 times 1 plus. This is supposed to say m over 6 squared. So you just plug it in. And here, we won't worry too much about simplifying. So say 1 minus 2 over 6 squared plus 1 6, 1 minus 1 over 6 squared plus 1 6, 1 plus 0 over 6 squared plus 1 6, 1 plus 1 over 6 squared plus 1 6, 1 plus 2 over 6 squared plus 1 6, 1 plus 3 over 6 squared. And you start to get the feeling like, oh, that's why we want some notation. Because it would be terrible to write that down. And you can imagine if we had 100 terms. Hopeless, hopeless. All right. So, some basic properties of sums. Some are not very surprising, so here's some sum properties. So remember, when we talk about sums, it's adding. And so when you're adding a bunch of terms, it's easy to move stuff around. So if you add a bunch of terms, CAK plus BDK, you can say, look, I'll separate over to the addition, and I can pull out the constants. And that's because addition is nice. We like addition. The fancy word is that it's linear. We've already saw an example of reindexing. So it is possible to reindex and have the same sum. It's just a convenient way in most cases. We won't have to worry too much about that, but just want to point that out. Now, we mentioned that when we write down a sum, we have many terms. What would be nice is to say, oh, we can actually go and collapse that and find a nice simple expression. So I have here a couple of sums, and I claim these are all true. We'll prove some of them. So the first sum here in green says, suppose we sum from 1 to n the number 1. Now you might say, well, what is that? Well, that's 1 plus 1 plus 1. Because right, every value for k, we always are adding 1. How many times do we add 1? N times. So if you add up 1 n times, what do you get? You get n. So that's what the first sum is saying. And that's where you're saying, like, I believe this. If I add up 1 17 times, I get 17. Cool. Now the second one, you may have seen this before. So here, this is adding k. So this is 1 plus 2 plus 3, all the way up to plus n. Now, there's a couple of ways to visualize this. Here's one way to do it. We'll do it by dots. 1 dot, 2 dots, 3 dots, and I bet you can't guess what comes next. 4 dots! I know, it's crazy! I'll stop here at 5 dots, just to sort of emphasize. I don't want to get too dotty here. All right, now, I'm going to put the same number of dots, but go in the opposite direction. So 1 dot, 2 dots, 3 dots, 4 dots, 5 dots. Now, the question, how many dots? Well, if you count how many rows, you'd have n rows. Because for each thing we added a row. How many columns? N plus 1. So the number of dots is n times n plus 1. Well, how many of dots did we want to get? Well, we want half of them. And so, if I just want to add 1 plus 2 plus 3 all the way to plus n, it's half of n times n plus 1, which is what this says. The sum of the first n numbers is n times n plus 1 over 2. Okay, so that's that reason why that's true. We're going to skip this one because there'd be a whole lecture about why that's the case. We'll just accept it for now. Let's do the last one. This one's a fun one. So this is geometric. Now, oftentimes you hear the word geometric and you think, oh, I should draw a picture. That sounds geometric. But geometric has a particular meaning. It means multiply. So you'll hear things like arithmetic versus geometric. So arithmetic means you add. Geometric means you multiply. So what's happening is every time we're multiplying by another factor of r. So I have r, is the first term. Multiply that by r, that's r squared. Multiply that by r, that's r cubed. And keep going all the way up to r to the n. And let's call this our sum. Okay, so that's what we look like. R plus R squared plus ... up to plus R to the n. Now, the theme was you multiplied by R. So, let's embrace that theme. We'll go all in and say, let's multiply by R. So, let's take R times S. So, everything gets multiplied by R. R times R becomes R squared. R squared times R, R cubed. And then we'll continue. R to the n minus 2 times R, R to the n minus 1. R to the n minus 1 times R, R to the n. R to the n times R, R to the n plus 1. So every term got an extra factor of R. We essentially just shifted over. Now, what can we do here? We'd like to have not very much. So our secret goal is we'd like to somehow remove the middle. And we say, gosh, what do we notice about these two? Maybe we don't say gosh, that sounds very 1950s. What do they say nowadays? Gee willikers? But anyways, what can we do? Well, we can cancel. How do we cancel? Subtract. So if you take, for example, R times S minus S, you'll have 0 subtract R, so you get a negative R. Cancel, 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 cancel. I feel like I'm part of cancel culture now. And then on the end, R to the n plus 1. So that's all that's left. So the last thing is factor an S out, and you get R minus 1 times S is R to the n plus 1 minus R, or S is R to the n plus 1 subtract R over R minus 1, which is what we claim. Okay, so those are some basic sums, which we will use. Now, the punchline for today, our last slide for today. There's a lot to see here, and we're going to come back and revisit this. But let's recall, we use a Riemann sum to find the area below the curve y equals f of x between a and b. And we're going to use n equal subintervals, always use the right hand point. So I have a to b. I'm going to split it up into lots of n equal parts. So the area is I'm adding up the areas of the rectangle. So that's the sum. So I'm adding the n rectangles together. So I have my first rectangle, my second rectangle, so forth and so on, all the way to my nth rectangle. F of xk is the height. Delta k is the width. So they all have the same width. So what do you do to find the width? How far did you go to get from A to B? Well, B minus A. How many pieces did you cut it up into? N. So the width of every single one is B minus A over N. So B minus A over N, that's the width of a single interval. Now, how do you find the endpoints? Well, what you can do is you can say, I'll start at A, and to get to the first endpoint, I'll just move over one width. So when k equals 1, I'll have A plus, I moved one width. When I want to get to my second, I'll move over 2 widths. So that's k equals 2. When I get to my third interval, I'll move 3 widths over. And in general, the right-hand endpoint is you start all the way at the left, and you say, move over the widths the right number of times. So we say, aha, our area is our sum. 1 to n, f of a plus k times b minus a over n. These are our, where we plug it in. So here are our heights. Here's our width. Now, This is an approximation. We don't want an approximation. We want the exact thing. So how do you make better approximations? This gets back to last time. How do you zoom in? More rectangles. More rectangles. Well, how many? All of them. We want as many rectangles as you can. You say, well, I can always make more. Then do it. So what does that mean? We're going to make infinitely many rectangles. So we're going to let n go to infinity. So our area, as n gets big, our approximation becomes an equality. It's the limit as n goes to infinity of a Riemann sum. This Riemann sum. Now, your initial reaction is going to be like, ugh. That's a correct reaction. But we're going to do a couple of cases next time to show how this works. And then we're going to be like, huh, isn't that interesting? And then the fun begins. And that'll be next 2 lectures from now, is the fun begins. All right, thank you.